Welcome to another CCOM-JHC seminar. Today's seminar speaker is Dr. Laura Brothers. Laura is the National Energy Technology Laboratory National Research Council Methane Hydrate Fellow. She's working at the Coastal and Marine Science Center at the USGS down in Woods Hole, working on mapping the Arctic subsea permafrost. She's a newly minted PhD, having gotten her PhD from the University of Maine in August of just last year, working on seafloor Pockmarks that she'll be talking to us about today. And also at the University of Maine, she completed a dual master's in oceanography and marine policy, and she holds undergraduate degrees from Bryn Mawr College and West Virginia University.
Thanks, Monica. Well, thank you for having me. Today I'm going to talk about some results from my dissertation research. The image I have right here is the seafloor of Belfast Bay, Maine. These craters you see are the Pockmarks.
You have to put the mouse over on the.
Yeah, so just
okay. Awesome. Okay, so so the outline of the talk. First, I'm going to introduce you all to Pockmarks. I'm going to talk about Pockmarks principally in the Gulf of Maine, Bay of Fundy coastal areas today. I'm going to go over what makes a Pockmark, looking at the origins of Pockmarks by looking at the stratigraphy. I'm going to go over how Pockmarks are distributed, looking at spatial distribution, and then how active are these fields. Pockmarks are seafloor craters. They're found in muddy settings. They're found all over the world. These red dots you see, those are Pockmarks. Generally, Pockmarks are associated with fluid escape, and methane is thought to be the driving fluid in most of these areas. But the driving mechanisms are uncertain for how this methane is released, or how these large craters are formed, and once they're formed, how they're maintained. Several questions. So, conditions under which Pockmark fields are common. These are conditions where there's a lot of fluid coming out the seafloor. So areas that you have mature sedimentary basins where there's a lot of thermogenic hydrocarbons, areas of gas hydrates, deltas, and extensive tectonic activity. This image to the left is the Gabonese continental margin, and these are rather large Pockmarks. These are on the order of 1 kilometer in diameter. But here's another Pockmark field, and this is in Blue Hill Bay, Maine. And this bathymetry data was collected by the Ocean Mapping Group from University of New Brunswick. And just so we're all on the same page, some conditions not found in the coastal Gulf of Maine, Bay of Fundy area are deep thermogenic hydrocarbons, hydrates, extensive tectonic activity, etc. You get it. So fundamentally, we want to know, why do we get Pockmarks in this part of the world? Why don't we get them in other nearshore settings? Why don't we see them in Chesapeake Bay? Why do we get them here? And what can we learn from these Pockmarks that we can apply to the other Pockmark fields? And just so we all know, these Pockmarks can be quite large. They're generally about 84 to hundreds of meters in diameter in this region. This is a picture of Maine's Governor Mansion in a Pockmark, but you know, an Olympic-sized ice surface would also easily fit in a Pockmark. So, okay, yeah, you caught it. All right. So, looking at the coast of Maine, this is a regional distribution for where we find gas in the seafloor, and that's areas labeled in green, and areas labeled in black are where Pockmarks have been found. Generally, these have been found with side scan sonar or boomer seismic surveys. This map is also observation limited. We haven't been everywhere with our instrument, and it won't surprise you to know that Pockmarks and gas distribution don't actually just end at the United States border. They go well up into Canada and to the eastern side of North America. So this would be kind of a classic seismic line that we get in a Pockmark field area. These areas, you get curtains of acoustic turbidity. Interpret that as methane gas. This has been verified as methane gas through chromatographic analysis of some headspace gas. and there's ignitable quantities of the gas in vibrocores that have been collected in this area. So we know it's methane. Looking at the Belfast Bay Pockmark field, and this is the bay that we've collected the most observations on. Bay is inland, it's generally, at its deepest, it's about 70 meters water depth. And this area outlined in white is where natural gas underlies these pockmarks. So in these areas, we assume gas, or associate gas, with the formation of these large seafloor craters. Now, going over our sea level history and how maybe the gas evolved in these areas, on the left I have, right here we have the Maine sea level curve, and here's kind of a cartoon of the coastal evolution of the area. So, 15,000 years ago, there was a sea level high stand. The glaciers were retreating. Sea level was about 70 meters higher than it is at present day. During the time glaciers were retreating, they were depositing kind of rock flour, this glacial marine mud, as they were progressing. So right up here on our sea level curve. Just a couple thousand years later, the glaciers had retreated, the crust had isostatically rebounded, and sea level had dropped to 60 meters below present day sea level. So at that time, these areas that had been underwater, with this irregular underlying topography and this glacial marine mud, these would be ideal settings for things like lakes, wetlands, other coastal lowlands. These are all environments where organic, rich material can accumulate with some in concentrated sediment. Moving to present day sea level has transgressed. These areas are deposited with Holocene sediment, and we've hypothesized that this organic material deposited during lower stand has evolved into methane ostensibly responsible for forming the pockmarks. When we look at a seismic line in the area, we see a lot of the stratigraphy we just described. So looking for here, we have at the top, you can see the pockmarks. In profile, we usually have 10 to 40 meters of Holocene sediment over top. You can see a clear unconformity separating the Holocene from the Pleistocene, glacial marine mud, underlying it, irregular bedrock framing the sequence. We also see in Belfast Bay, we've identified a new acoustic unit that we find in between irregular topography, in between the subcrop and to the side of the field. We hypothesize that that could be maybe our paleo lakes or paleo wetlands that we talked about. To test that hypothesis, we went out with vibrocores in the area. So again, looking at the stratigraphy, so here is the layer that we would like to hit. But our vibrocores, vibrocores are only going to be a maximum of 6 meters in length. And generally, ours were even shorter than that, depending on what we would hit. If we'd hit the unconformity, which is very coarse-grained, we had an average vibrocore length of 3.4 meters. So it was unlikely that we actually intersected that unit with our surveys. But what we did find in locations marked with X's, so again, in the white, we have areas that are underlain by natural gas. This area outlined in the black is where we found that new acoustic unit. But the vibrocores I'm going to show you were collected right in this part of the field. So then these vibrocores, and these were consistent, stratigraphically consistent with the 3 cores collected right beside each other. In these cores, I was hoping to find maybe a peat or something, like you might find in the salt marsh, but what I found were these very hard concretions of mud, indurated mud class. And I would find them underneath the Holocene sediment and at the border of the glacial marine mud. And actually, this glacial marine mud, which is typical of this area, you see it in coastal areas, it's steel blue, it's been reduced, it's been buried for a long time. But in our samples, we're finding it oxidized at the top of this unit. Pulling apart these nodules and what I was finding in these cores, we actually, this was a bit of a puzzle for a bit on what these were. They were made out of the same material as the Holocene mud, the same material mineralogically as the glacial marine mud, and they had very low organic content. It turns out these are a paleosol. You get these in wetlands. This is a hydric soil. These are called redoxamorphic features. So these features, these concretions, these beds of oxidate, these gradients of oxidation form by, you have to have seasonally saturated soils. So they're being reduced, but they're getting exposed to water on some sort of cycle, and you have to have transpiring bacteria. Now, maybe you're thinking you've never come upon a real hard plast, walking around. You haven't, because they're buried deep underneath the organic material. This is the O horizon of a soil. So your A and B horizons are your topsoils. So that's the organic type soil. That's the type of soil you want to use in your garden. That's the type of soil that you're seeing in the woods. And that's where your organic content is held. So what I was finding was the bottom, less organic content of essentially a marsh that had been eroded away. So, knowing that that soil had formed in this sort of wet, seasonally wet environment, we proposed that this could be a modern analog for some of these pockmark fields. But when? When was it like this? And does that have anything to do with pockmarks necessarily? Again, looking at the sea level curve, so this green is where I find the paleosols generally 20 to 40 meters below present day sea level. And they occur at the unconformity, the transgressive unconformity, so I put them just before the Holocene. You know the paleosol with the organic matter had to develop at a low stand in sea level, and we know that the paleosol was eroded during the transgression, and we know the pockmarks formed after that transgression. So the pockmarks formed and developed in material that was not overlying a concentrated source of organic material, because those organic upper layers of the soil had already been eroded by the Holocene. So this suggests that you don't need a buried lake necessarily, or a buried wetland to get the methane required to suspend the soil. So, potential for buried lakes and wetlands might not be what makes this region unique for nearshore pockmarks. It might be something else. So, moving away from that, we start to look at, well, where do we find these pockmarks? So this is the Passamaquoddy Bay pockmark field. And if we start to look at the pockmarks as point features, we can start to do some spatial analysis on them. And we start to see that pockmarks are non-randomly distributed. And Passamaquoddy Bay, you can kind of just even see here some topography. That's a drumlin. You have the lines of pockmarks. In Belfast Bay, you can do a nearest neighbor analysis, and the pockmarks are in clusters. You generally find the pockmarks most tightly clustered around kind of small basins under the present day seafloor, and along irregular topographic highs. So we're able to say something about the relationship to where pockmarks are with sediment thickness. You get, there does seem to be some control over that. You get bigger pockmarks in thicker sediments. You get smaller pockmarks on the outskirts. Now part of this, that relationship makes sense because the pockmarks are only in Holocene sediment. We know this from the stratigraphic record. They have to be in the Holocene. So you wouldn't find large pockmarks in thin Holocene sediment. But you don't find small pockmarks with large pockmarks. You You get large pockmarks in your deep sediments in the center of the field with your deep basins, and you get your smaller pockmarks on the side. If looking at these fields, if you look at the major chain of pockmark fields, those are generally related to a nearshore basin. And so, just to show you something. So these seismic lines can correlate to where these arrows are. And as you can see, this chain of pockmarks just follows this irregular high at this point. Well, so you looking at this, looking at subsurface data, looking at the spatial analysis, can determine that pockmark distribution does relate to the underlying topography. We have these nearshore basins where we seem to get clustering of the pockmarks. These basins provide accommodation space for accumulation of sediment, of eroded sediment. They provide space for sediment accumulation or consolidation. And they could be providing a fluid focusing gradient which enables the fluid to escape, forming these large craters. We start to look around in the world. The other places we find nearshore pockmark fields are in environments like fjords and fjords, the rias, the bedrock-controlled rias of northwest Spain, and this coastal area here. Those are all areas that have bedrock-controlled, irregular coastlines, and you find your pockmarks around their steepest change in relief. So, just some conclusions on this section. I think, what produced this area? Well, it was a transgressive environment. So you had a wetland that was being eroded. And although there wasn't a concentrated source of organic material that was buried like a wetland, that wetland was eroded. That organic material would have been introduced into the water column. Some of it would have been biologically taken up, but in general, it would have been kind of an organic, rich depositional area. Is there something unique about this nearshore setting? I would say that it has to do with the pockmarks distribution related to the underlying topography. That we're getting these around topographic highs, and we're finding these in the basins. And if we compare with where we find pockmarks all over the world, another place we find pockmarks, this is an offshore setting, but you get them in lakes, which are also basins. And so, starting to think that bedrock may, and underlying topography may fundamentally control where we get these sort of features in absence of massive fluid venting associated with hydrocarbons, etc. So, once we have this pockmark field, how active is it? And by active, I mean, is this field still venting fluid? Is it venting methane, etc.? And is this venting disrupting the seafloor in a way that we would be able to measure? Are we forming new pockmarks? So, Belfast Bay has been looked at for the past 20 years to see if we're forming new pockmarks, and some observations that would indicate this is an active venting field. Mud plumes, and you find these in this bay, but all over the region, mud plumes in the area. In 1989, Joe Kelly went over the area with a side scan sonar and found a plume jetting out of the seafloor. He interpreted this as something analogous to what would form a pockmark, this fluid escape. If we look at the pockmarks, they have very steep side walls. On the order of 30 degrees. Sometimes it's more like 40 degrees in some of these pockmarks. This area is a disturbed estuarine setting close to a river. That slope is pretty steep for something to be preserved that long. This was interpreted, these steep slope walls were interpreted as a sign of the field being active, because why would these steep walls preserve unless there was fluid coming out of the pockmark maintaining these walls? Other observations, mud plumes from ROVs. There was turbidic flow within the pockmarks, which would indicate the walls are weak. And there were new pockmarks identified in repeat side scan sonar surveys throughout this area. But there might have been some error, there was error associated with the position of those surveys. But not everyone thinks these pockmarks are actively venting methane. In 2003, there was a geochemical survey of the area, which was looking at the sulfide profile in the sediments. They were using 1.1 meter long gravity cores, and they found no overwhelming evidence for abundant methane in the area. They found methane in the kind of orders of magnitude that you would expect to find in most coastal settings, but not that much. So they interpret that these pockmarks may be inactive. I wanted to know how long the pockmarks had been there, and dating pockmarks in this setting is problematic because you might be able to date material, but knowing how that material relates to the morphology of a pockmark is not direct. So to begin with, I looked at bathymetry, historical bathymetry records. And so this is the smooth sheet from a 1872 survey collected by the US Coast Survey. And this is a survey, you see the denser spacing fathometer lines collected in 1942 over the same area. Outlined in black here is the 60-meter contour and the 60-foot contour and the 100-foot contour. Those were actually, I traced those. Someone from, presumably associated with the surveys had made those contours back to fill in the blanks, but they picked out holes throughout this area and made note of it. Looking at the descriptive reports, I felt a real kinship with some of these hydrographers as they were not quite sure how to initially characterize the seafloor. But in 1948, they were clearly making notes that these were holes in the seafloor, and so they were around here. We look at the 2006 bathymetry collected in the area and put the contour lines around it. I would say that these contours along the sides here, where the data has a more dense spacing, follows well with some of the pockmark chains in that area and generally kind of captures some of the shape. So we know the pockmarks were there at least, I would say in the 1870s, though we can't be sure about their distribution, how it compares with today's. Looking at more modern data, so this was a 1990 survey collected by NOAA in the area, and it clearly resolves the pockmarks. And we went out in 2006, imitating the survey with the correct line orientation, getting 100% coverage, an interferometric side scan sonar, we found that all of the pockmarks surveyed in 2006 were present in 1999. We went out in 2008 for some similar coverage with the same setup from 2006. No new pockmarks in this time period within the resolution of what we compare the data sets at. Each data set was gridded to 5-meter resolution. There were no missing pockmarks, and there was no obviously altered pockmarks. They had not grown, they had not shrunk, none had disappeared. If we were looking at the seafloor, curious to what the seafloor was doing, I took cores throughout it looking for cesium and lead-210 dating. What we see is pretty spiky data. Oftentimes, the cesium spike, you're looking for a spike in cesium, and you might say that's 1963, and you might generate a sediment accumulation rate based on that point. But as I pointed out here, these data are very spiky, inside pockmarks and outside pockmarks, and our lead-210 never goes back to the background levels, so I was uncomfortable attaching any kind of age model with these data. I think these data are robust examples that this is a disturbed area. We're looking at the undrained shear strength of the near bed sediment. These values are in kilopascals, and there are no values that exceed 7 kilopascals. That's very weak. That's essentially strengthless fluff sediment. And so we would expect these pockmarks, why don't they fill in? So just based on these, I think we conclude that it's easy to say large-scale sediment resuspension and dispersion related to the pockmarks does not happen in this field. Other mechanisms besides near-bed sediment strength would have to be at play on what is keeping these pockmarks open. And the abundance of the pockmarks and their size in this field, but yet we did not observe any venting in our surveys, suggest that pockmark size and frequency do not reflect modern venting activity. Thus, if you have a very pockmarked field, you shouldn't necessarily think of it as a very active field. And just kind of in summary, so what might make these settings unique from non-pockmark areas? Well, transgressive environments with abundant organic material that can be eroded and introduced to the system, irregular underlying topography. What could be applied to other pockmark fields? Looking for a transgressive setting, perhaps, and irregular underlying topography might be what a unifying feature with other nearshore pockmark fields. And the activity expectations, which would be episodic at best or minimal. And so that I will take any questions. That was kind of short for a Friday, but it's been a variety week. So. Yeah.
Are you seeing any kind of biological activity within the pockmarks? Perhaps fish maintaining them as breeding holes or?
So a couple of studies have been done on the biology of this region's pockmark fields, and generally what they find is that, so first of all, if we were thinking that these were really venting a lot of methane, you might find some creatures that need methane to live, that live inside of them. And that has not been found in the area. But fishing practices, they are pockmark specific regionally. In Belfast Bay, the fishermen preferentially fish in the pockmarks when the conditions are right. Now, I think that could be for a number of reasons. There would be turbid, well-mixed areas within these pockmarks. There are basins. You get coarser material debris, which lobsters like. But in other fields in the region, fishermen that fish there avoid the pockmarks and call them death holes. But generally the fauna that are found in pockmarks from the biological studies they're disturbed fauna, they're fauna that live in disturbed environments, but they're not methanotropes necessarily. Yeah?
The mud around the pockmarks, is it cohesive? Does it have talking about the slope and maintaining that for years, that's the question, if there's anything that like worms or something.
Right. So, so it's fine grain mud. It's mud, and so fine grain. It's a disturbed area, and when we were taking shear strength values, so we don't have a cohesive. I didn't measure cohesiveness, but I measured undrained shear strength, and the strongest value we got of 7 kilopascals was taken on a pockmark wall, so a core on the wall, which could reflect you've hit more consolidated material that has more strength. Generally, fine grained sediment can maintain a steep wall in some settings, thinking of, say, banks, river banks, etc. But if it gets disturbed, it falls apart. Generally, these steep slopes. So, from our measurements, the material is not particularly cohesive, but I think to get the strength of these pockmarks could be held by deeper within the sediment floor, several meters down. And when you're building, say, foundations for oil rigs, etc., and they're trying to get a handle on sediment strength and cohesiveness, they have to take very deep samples. Yep.
Well, you said that the pockmarks had a spatial distribution that you correlated with either topographic highs or thicker underlying sediments. But did I miss what you said? I mean, some of them clearly have turned into, a bunch of pockmarks have turned into a line. Did you say anything about that?
So, generally, so first, just how we picked out the pockmarks. was not just visually, we automated it by, we picked the point that represented Pockmark based on flow within the DEM, and so essentially all our points were sinks. And so when we have a line of Pockmarks, they're still individual Pockmarks, even though they are in a line, because they had to have some flow going to, in a kind of a watershed model, to the bottom. But certainly, once you establish, particularly with a north-south kind of trending chain in this area, the tidal currents could certainly help erode such a feature. But those chains generally go right along topographic highs. You get them at the maximum change in Holocene sediment thickness.
I'm just curious, you're talking about a spike in the cesium representing 1963. Why?
In the region, based on, that was the, where they were doing all the nuclear testing in the region, and so that's generally, so in coastal areas, salt marshes, etc., you can usually see 1963 pretty clearly in your record. And if you have it over time, it sticks out. So that was the reasoning for that.
What's the shallowest depth you've seen of Pockmark?
You, within 12 meters of water. And so, but just getting to their scour real quick, I just want to show you kind of the full picture of a field. And so here's the top of the Pockmark field. You have chains, Pockmarks, and you go through here, a Thawing, that Pockmark can clearly be modified by strong unilateral currents in the area.
Okay, great, thank you.
Great.